Hey everyone, I'm going to walk you through lesson 5.6, and the first thing I need to do is share my screen. Um, all right, let's consider this problem. We've got bananas being loaded onto a truck. We have a function which tells us how many bananas are on the truck at time t. This is called an accumulation function because it's telling me the accumulation of bananas on the truck. Um, So what would f of 7 minus f of 1 represent? Well, f of 7 is the number of bananas on the truck at time 7. This is the f of 1 is the number of bananas on the truck at time 1. So this is the number of bananas loaded between the times t equals 1 and t equals 7. Now it's just the number of bananas loaded. There might have been bananas on the truck before time t equals 1. So it's how many were loaded over that time frame. All right, so keep that in mind. We'll come back to that in a minute. Now we want to look at this right here, the integral from 1 to 7 of the derivative of f. Now I need to think about what f prime of t represents. So if f is the number of bananas on the truck at any time, f prime, a derivative of that, is a rate of change. So it's the rate at which bananas are being loaded at time t. Okay. So what would the integral of this rate function tell me? We're going to approximate it with a left Riemann sum. We're going to go from 1 to 7. Here's some function. If I do 3 rectangles, then I divide it 3 and 5. And so this rectangle, my 3 rectangles. All right, the area of the first rectangle would be the function at 1, and remember the function is f prime. I should maybe write that up here. This is f prime of x. So that would be giving me this height, and the width is 2. Now, f prime of 1 is the rate at which bananas are being loaded at time t equals 1. I'm going to use that to approximate the rate that bananas are being loaded from time t equals 1 to time t equals 3. And then the area would be the total number of bananas loaded between t equals 1 and t equals 3. It's an approximation of the total number of bananas loaded over that time frame. The second rectangle, I'm going to use f of 3. I'm going to use this height. Again, that height is representing the rate that bananas are being loaded at time 3. I'm going to use that rate to approximate from 3 to 5. And if I multiply by the 2 minutes, the rate at which bananas are being loaded per minute, times 2 minutes, that's how many bananas are loaded between t equals 3 and t equals 5. All right, and the third rectangle, basically the same thing, right? It's the rate at which they're being loaded at time 5. And I'm going to cheat a little bit here. Duplicate, put it there. Just change my times from 5 to 7. Okay. So the entire area underneath the integral of f prime of t is telling me the total number of bananas loaded I add up how many are loaded over every 2-minute period, then I get how many are loaded over the 6-minute period between t equals 1 and t equals 7. But hey, wait a minute. That was right here. Same exact thing. The number of bananas loaded between t equals 1 and t equals 7. So what does that mean? That means the integral from 1 to 7 of f prime of t dt equals f of 7 minus f of 1. So this is the derivative of this function. Of course, what integrating indefinite integrals, we said, hey, figure out which function you took the derivative of to get this function. That's your answer. So I'm going to use that concept now, and I'm simply going to evaluate that function at my limits of integration, and that gives me the exact area underneath the curve, which, if you think about it, that's kind of ridiculously easy. All right, this is called the second fundamental theorem of calculus. There's a first fundamental theorem, although books disagree on which is the first and which is the second, so it doesn't really matter. It's a fundamental theorem of calculus. And basically just says, if you have a function, find its antiderivative, evaluate at your endpoints, your limits of integration, and subtract. So let's do it. So the integral of 3x minus 2, I just like, okay, how would I, what function did I take the derivative of to get that? So I just integrate. Well, that's 3/2 x squared minus 2x. Now, the way that I do the notation here is that I use square brackets and I put the 2 and 7, my limits of integration there. And then I'm going to plug in. Okay, I'm plugging in 7 for the x values. Then it's minus, and then I plug in 2 for the x values. Okay. If you do that math, you'll end up with 147 over 2 minus 16. I trust you guys can do the math. Okay. Just to point out, the long way to do this was to do that limit as n goes to infinity of the sum of I from 1 to n. We did this to find the area between the curve of y equals x squared and the x-axis from x equals 0 to x equals 4. This is a problem from lesson 5.5. Now, I would just do like, okay, I'm going to go from 0 to 4 of x squared dx. I integrate x squared, 1/3 x cubed, evaluate from 0 to 4. So I'm going to plug in the 4 and the 0 and subtract those two values. Obviously, the second term is all just 0. And hey, look, yes, they are the same. Obviously, this is a much nicer way to find definite integrals. All right. So let's just do a couple examples. Find the following definite integrals. X squared, if I integrate, it's 1/3 x cubed. The integral of 2x is x squared. The integral of 4 is 4x from 1 to 3. So I'm going to plug in 3 for x minus, and then I plug in 1, 1/3 times 1 plus 1 minus 4. And if I do all that math, you should end up with 26/3. Okay. Integral of sine is, well, integral of sine is cosine. Is it positive or negative? I hope you said negative. From pi over 6 to pi. So it's minus the cosine of pi minus cosine of pi over 6. All right, cosine of pi is -1, so minus -1. The cosine of pi over 6 is power 6 cosine root 3 over 2. So negative root 3 over 2. So that's 1 plus root 3 over 2 would be my answer. All right, the integral of e. That's just a constant, right? So that's just going to be equal to e times x from -4 to 4. So that's 4e minus, now plug in -4. So those become a plus, and your answer is just 8e. The integral of u plus 2 times u plus 3. You got to do something before you can integrate. Hope you remember you have to FOIL. All right, so that you can use the power rule, you have to have a sum of powers. When we have a product of two functions, we can't just integrate each function and then multiply their antiderivatives together. So u squared, 2u and 3u is 5u plus 6. So that's 1/3 u cubed plus 5 halves u squared plus 6u from 0 to 1. I did pick relatively nice numbers. Just plug in 1 and then plug in 0. And of course, that's just going to be a big fat 0. So that would be 2, 6, 5 halves would be 15, 6 plus 6. Do I have that answer? Should be 53, 6. Okay. All right. Remember here, when you're dividing two functions, you cannot just take the antiderivative of each one individually. You have to get it down so you can just use the power rule. So it's 2 over root x plus x squared over root x. So you just divide it, make it two fractions. So that's 2x to the -1/2 plus, so that's x squared and then -1/2. So that's 3 halves, right? Okay. Integral from 1 to 4. So integrating, I add 1 to the exponent. I multiply by the reciprocal of that exponent. X to the 3 halves would become x to the 5 halves multiplied by 2/5. Evaluate from 1 to 4. Plug in the 4. So I have 4 times 4 to the 1/2 plus 2/5 times 4 to the 5 halves. Now plug in the 1. That's just going to be 4 plus 2/5. 4 to the 1/2 is 2. 4 times 2 is 8. 4 to the 5 halves, the square root of 4 is 2. 2 to the 5th is 32. Minus 4 plus 2/5. If I combine that 8 minus 4, that's 4. Combining the fifths, I have 64/5 minus 2/5. So that's 4 plus 62/5. That would turn out to be 82/5. Okay. Integral of cosecant squared. Do you remember what that is? It is minus cotangent x. Just from pi over 4 to pi over 3. So you do need to know your unit circle, folks. Minus cotangent of pi over 3 minus cotangent of pi over 4. Minus 1 over root 3 plus 1 if you work that out, knowing your unit circle. Okay. Let's calculate this one. So this would be x to the -2 dx. No. Okay. X to the -2, add 1 to the exponent. So that makes it x to the -1. Multiply by the reciprocal of -1. All right, so minus 1/3 minus -1, I believe that's what we got. So, so that is -1/3 minus 1. That's -4/3. Okay, let's think about the graph though. The graph of 1 over x squared looks like this. So it would be this area plus that area should equal the definite integral. Notice those areas are above the x-axis. Therefore, how did we get a negative number? All right. Well, the thing is, your function cannot have an infinite discontinuity. If it does, you cannot use this shortcut method. So make sure your function does not have an infinite discontinuity in the interval that we're looking at. Okay, so that's an important rule. All right, a couple little questions here. Excuse me. If the integral from a to b of f of x dx equals f of b, and here it says it equals g of b. Well, how could that be? Well, remember, a function has multiple antiderivatives. So, for example, the integral of 2x dx, right? It equals x squared. But hey, it could also be x squared plus 3. Remember, it was x squared plus c was the general. There are multiple antiderivatives. You can pick any antiderivative. We usually pick the one where c is 0, but you can pick any antiderivative to do this. So if these are equal, does that mean f of g of x equals f of x? No, they can differ by a constant. But if they're both equal to the integral from a to b, then are their derivatives the same? And that answer is yes, because, right, if they differed by a constant, that constant would just go away when you take the derivative, and then they would be equal. So basically saying here that like the derivative of x squared and x squared plus 3 would be equal. All right, we got one more little fun problem. Here, an infinite Riemann sum. And we want to figure out this is equal to what definite integral, and then use our newfound shortcut for finding the answer to this limit. So this one is a little bit weird because like you don't see that something over n, which is telling you the width of each. But noticing that this is to the 4th and that's to the 5th power, it's like, oh, maybe I should factor out a 1 over n. So let's do that. So 1 over n, I to the 4th over n to the 4th minus I over n. Well, that's looking more like what we're used to seeing. So this is equal to the definite integral. I don't see any shift, so I'm starting at 0. The 1 over n tells me the width is 1. And then this would have been x to the 4th minus x dx. So to find this limit, I can actually integrate 1/5 x to the 5th minus 1/2 x squared from 0 to 1, 1/5 minus 1/2 minus a big 0. We love it when 0 is one of our limits of integration. It turns out usually pretty nice. 1/5 minus 1/2, so that's 2/10 minus 5/10. I think that's -3/10. That is the answer to that limit. Okay, that is exactly the answer to that limit. All right. And then the last thing is that your calculator can do a definite integral. Use the Math 9 function. Um, Most of your calculators will probably be in this kind of um, setup, and you just plug in the limits of integration and the function you're integrating and the dx. Um, so try it. If yours isn't, then this is the how you do it. The answer would be 3.66 08 if we do 4 decimal places. You always give 3 decimal places. You can either truncate or you can round. So we can say 3.660 or 3.661. This one you should be getting 1.0736. So you can say 1.073 if you just truncate, or if you round, you can say 1.074. All right. That's it, folks. I hope. Let me stop sharing my screen. Okay. I think that's good. All right. All right. Like I said, let me know if you have questions, guys, and I will see you soon. Bye.